Aloha, everyone, and welcome to the Michaelani Center, the Advanced Technology Research Center. I'm Dr. J.D. Armstrong. I'm the Maui Technology Education and Outreach Specialist. And usually when I give introductions, I get a mistake or two that I get to make, and so I hope I get that even though I'm introducing myself. Because, when you're making up the stories, you have to remember what they are, right? And I can't remember what they are. I have in physics from Westminster College of Salt Lake City. I was born and raised in Salt Lake City, and then I went to Michigan State University, where I was studying physics and working in particle physics, nuclear physics, and was quite interested in quantum chaos. And it was sort of the mathematics of it that really got me excited. Until I took a class in general relativity for fun. And the professor of that class is Dr. Jeff Kuhn, who some of you may know is one of the scientists who works here at the University of Hawaii. And I started working with Jeff after the class, and when he took a position at the University of Hawaii, I followed him out here and got my PhD in astronomy from the University of Hawaii. And then I came over to Maui to work with the University of New Mexico. And next thing I know, the University of Hawaii had hired our entire group, and here I am today. So I mostly work with a lot of students, very young, basically young scientists, and they're doing some really incredible work. A number of them are here tonight, and we'll give them a round of applause. Yeah. Okay. And so I'm going to be talking about Here and Back Again, an astronomer's tale. All right. Are the lights in back okay, or are they problematic? Oh, and I should get a picture. We got to prove that their audience is here. My boss likes that. He's always complaining that he doesn't know about these things. Okay. Oh, I'll turn the lights back on. Everyone that's watching the live streaming is looking at me going, "What is this guy for real?" Okay, yes. Thank you, everyone. Thank you for your patience. All right, and Hayden, you'll wave at me if the sound becomes problematic or if I walk out of the light. Everyone remind me to walk into the light. Go into the light, JD. So, There and Back Again, an astronomer's tale. What? No one? This is a friend of mine, Donna Womack. She painted this just for this presentation. Isn't that awesome? Yeah. Okay, so what is an astronomer? Well, astronomers are generally solitary creatures. They spend long nights in observatories, far away from the hustle, bustle, and lights of others. Now, observatories aren't these cold, dark places that you might imagine. Well, they're cold because they're on top of a mountain, but we wear coats. We have nice warm coats to keep us cozy, and they're dark, but that's okay. We like the dark. So they're actually rather pleasant places to be, and for some of the amateur astronomers in here can confirm that they're actually some of the nicest places to be. Absolutely wonderful place to spend an evening. All right. So, and then as the astronomers look through their telescopes, they see some amazing things. This is the Crab Nebula and Messier 82. This is a spiral galaxy. They see stars being born, and they'll see stars dying. And they'll see exoplanets. This is what I was talking about a little earlier, where we measure how bright the star is, and as the planet passes between us and the star, we can see the shadow. We can measure the difference in brightness. And so when you're seeing all these amazing things, naturally you're going to start thinking. And what are you going to think about? E.T., yes, that's one thing. And how do we get there? Okay, now astronomers also have a tendency to like science fiction because, science is what they do, and fiction about what they do is I guess we lean towards that. So we start thinking about ways to get there. And there are movies and TV shows and other movies and even other TV shows. Or maybe those were movies, I don't remember. Flash Gordon. All right. So we start imagining how we might get out and visit these places, how we might go out and see them. Well, we need to plan before we go. And so we can't really count on inns to be between here and there. We probably can't count on even gas stations. Okay? And only in Hawaii do you buy gas station sushi, right? We need to be well supplied for the journey because we're not going to get any sushi out in between the stars. And so one of the first things we need to determine is how far do we go? And we need to know this very well because if we miscalculate, we could be in serious trouble. Okay? So, the first thing we did to measure the size of the solar system is we observed the planets, the positions of the planets in the sky. And so Mars, for example, watch how it moves across the sky, and we realize that's not a star, that's something. And you start to watch, Mars will go all the way around the ecliptic, all the way around the Earth in the path of the sun. And when it's in opposition, when it's far away, when it's on the opposite side of the sun from us, tends to do this zigzag motion called retrograde, moves back and forth. And by measuring the angles of that, we can say, well, Mercury only gets this far away from the sun. So we know it's an interior planet. We know it's closer to the sun than we are. And because of the angle, we can say that Mercury is 0.387 astronomical units from the sun. And Venus, which is another interior planet and is also is closer to the sun than us, well, its distance from the sun is 0.723 astronomical units. Okay. Now, what is an astronomical unit? Well, that's the distance between the sun and the Earth. Okay, we're assuming circular orbits just for this discussion, but when this is really done, we do remember that they're elliptical orbits, and we factor that in. We then realize that Mars is 1.52 times the distance between the Earth and the sun, 1.52 astronomical units, and Jupiter about 5.2 times the distance from the Earth and the sun, so 5.2 astronomical units, and so on. We can determine all the distances to these planets in this very peculiar unit. But we still don't know what an astronomical unit is from these measurements. So we need to look at the universe in a little different way in order to figure out what an AU is. And so one of the first ways that this was done was by measuring the transit of Venus. By looking at when the transit began and ended at different places on the Earth, different points on the Earth, we can determine how far the Earth is from Venus and how far the sun is from Venus. Okay? It's a little bit like parallax, and I'll get into parallax a bit more in another slide or two. Once we've determined that, then we can start to say, well, it's this many miles to Mars and this many miles to Jupiter. Another way we can do that is we can look at Jupiter. Now, Jupiter has these 4 moons, the Galilean moons. And those moons orbit Jupiter have very precise timings. We can determine when they will pass in front of Jupiter and behind Jupiter. Well, when we're on the same side of the sun as Jupiter, these transits occur about 8 minutes earlier than predicted. When we're on the far side of Jupiter, they occur 8 minutes after predicted, about. So what would cause that? Yeah, the distance, how long it takes the light to travel. So when we're closer, we're about 8 minutes closer to Jupiter when we're on the close side. When we're on the far side of the sun from Jupiter, we're about 8 minutes farther. This was actually used to measure the speed of light. This was one of the first ways to measure the speed of light. But now that we know the speed of light very well, we can use this to verify the distance between the Earth and the sun. Okay? Another way we can measure the distance between the Earth and the sun is by using radio dishes. We can send out basically a radar pulse. So we send out a pulse of radio waves, bounce it off something like an asteroid, and wait for the pulse to come back. And then we know our distance to that asteroid or any other object that's orbiting the sun. And by doing that, we can measure the distance to the planets. And we can do this very precisely. We do this all the time with airplanes. So we can do this very, very precisely, and it's very well-known science. Then to confirm that, we've sent out spacecraft. NASA has sent a number of probes all over the solar system, and they get out to Jupiter, and they're a mile off. They wouldn't be able to do that if our measurement of distance to Jupiter were wrong. So we've well confirmed the size of the solar system. And it's a good thing, too, because we'll need to know that to determine anything outside of the solar system. Yes? Well, it depends on, how we're aligned, but so the question is, how long would it take a radar signal to bounce off a planet and come back? Depends on how they're aligned around the sun. But, for example, let's say Earth and Mars, and let's say they're lined up straight. So they're the closest they come, so that's 0.52 astronomical units. And it takes 8 minutes for the light to get from the sun to the Earth. So 8 minutes is 1 astronomical unit. It would take about 8 minutes to go out and back, somewhere in that neighborhood, as a minimum. But it'll vary. It goes up from there. Okay? No, 8 minutes, because it's half there and half back. So 4 minutes there, 4 minutes back. From Earth to Mars, yes. Yes. Okay. Good. I'm glad you're keeping me on my toes. Usually I'm the one that's confused. That's different. Okay, so we've sent these spacecraft out, and we've confirmed the distances. And we can also, once we have a satellite out there, it's even easier because we can figure out the delay and talk time to the satellite. So, how long would it take to Mars? Okay. So if we calculate how fast an airplane flies, it would take somewhere in the neighborhood of 9 years on an airplane to get to Mars. 9 years. Okay, about 600 miles an hour. And this is just measuring the shortest distance we could possibly fly. Okay. The space shuttle would take something like 115 days. Space shuttle's a lot quicker, much faster. And then the fastest thing that people have made is Helios 2, the Helios 2 satellite. It would still take about 13 days to get to Mars. So Mars is a long way away. Okay? So, in NASA, I looked around and looked at missions to Mars, and what NASA said. They said a mission to Mars would take somewhere in the neighborhood of 180 days. Okay? 180 days to get there, 180 days to come back, and then you have to stay there for about 18 months to get a good launch window for the return to Earth. So there we go. There's there and back again. That's what it would take just to get to Mars. 2.5 years. All right. So now, most of the things I'm looking at are outside of the solar system. How do we determine the distance to those? Well, what we do is we look at parallax. We do parallax. And for those of you in the internet audience, find something a little farther away than your screen to do this with. But everyone here, if you'll hold up your thumb at arm's length, close your right eye, and put it right over my face. Okay, now I bet you're all saying, oh, that's much better. Okay, now switch eyes. Okay, you see how the thumb, yeah, lady over here is scared now. So you switch eyes and your thumb jumps. Okay, now restart it, but bring your thumb closer to your face and blink your eyes again. Switch your eyes again. Does the thumb move the same distance? Does it seem to jump? It seems to jump more when it's close in. Well, what we can do is as the Earth orbits the sun, we can measure the position of the stars. So this was actually recognized very early on when people were talking about what stars even were. And they looked for it, and when it was too small for them to measure, they decided, no, they just must be pinholes in the night or something. We don't know. So what we do is the Earth orbits the sun. We look at this nearby star, and we compare it to very distant stars. The distance won't seem to move very much. And then we look at the star in June, and then we look at the star's position in December, and we measure the position both times. And doing some geometry and some mathematics, you can calculate what the distance is in terms of the distance between the Earth and the sun. Okay? So now, just to be clear, stars do move around, and so we don't just measure at 2 times. And in fact, we don't just measure left and right. They tend to make sort of an ellipse on the sky. Okay? So we measure, these are some actual measurements of what the parallax might look like. And so this is 1/10 of an arc second. So if you hold your little finger out at arm's length, that's about a degree. 1 arc second would be 1/3600th of the width of your little finger. Okay? And this is 1/10 of that, so 36,000th of the width of your little finger at arm's length. That's how precise you have to measure the positions of the stars before you start getting to measure the parallax. But we do it. And there was recently there was a release from a spacecraft that's doing this called Gaia. And one of the students here is smiling very big because she's doing a project with Gaia data. Okay, so this is what we really see when we take these measurements. We see these kind of loop-the-loop things with a motion of the star superimposed on them, and we have to detangle that. But after detangling that, and these are all from Hipparchus, which was the precursor to Gaia, after detangling that, we can measure the distances to stars, and we believe they're fairly accurate. Okay. So, the distances to nearby stars. Proxima Centauri. So, this is the closest star to the sun. And we can actually see, Proxima Centauri is in a 3-star system, and we can actually see Alpha Centauri from here on Earth, or from here in Hawaii. So if you're in the internet audience and you're watching from continental United States, sorry, you can't see it from there, but we can see it from here. And so perhaps you want to go out with a star chart some night and see if you can find it. But check what time of year it's visible. But Proxima Centauri is about 4.24 light years away. That's a lot of kilometers. I think that's 40, a lot of zeros, kilometers. Okay. Sirius is about 8 light years away, between 8 and 9 light years away. And that's 81 with the same number of zeros. Vega is another a very bright star that you might be familiar with. Um, we're up to 25 light years, and probably most of you have been watching the news and seen this announcement of Trappist 1, which is just shy of 40 light years away. So let's see here. 1,000 million billion trillion 373 trillion kilometers away. Okay, so space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemists, but that's just peanuts compared to space. Of course, Douglas Adams. All right. So space, yeah, it's big. And when you look at the stars, it's sort of believable that they must be very far away. These are things like our own sun. Proxima Centauri, which is fairly, or Alpha Centauri. Proxima Centauri is a little tiny guy. We can't see it from here without a telescope. We can't see it from anywhere on the Earth without a telescope because our eyes are not sensitive enough. But Alpha Centauri you can see, and Alpha Centauri is a star that is a bit bigger than our own sun. Okay? But it's a star, and you've seen stars before, and how bright are the stars compared to our sun? Not very. That's exactly the answer I was looking for. Thank you. So, how far away would we have to put the sun? How many times farther away would the sun have to be before it got down that tiny little dot that we see in the star? Stop and think about that for a moment. That's how big space is. Vastly, mind-bogglingly big. Okay, so let's think about how long it would take to get to this Trappist 1. Okay. Well, an airplane is something like 3.8 trillion years. Pizza? No pizza. Yeah, the Domino's will not deliver at that range. Or that altitude, for that matter. Space shuttle. We're still talking 130 billion years. Helios 2, we're talking 14 billion. And so I'm going to change the talk of my title, if I may. Getting there, an astronomer's tale, because, you know, if we're talking about billions of years by conventional travel, coming back might not be an option. We might, the people that leave to go to there might not be the same ones that arrive. Okay? So, there's a project called StarShop. And the idea of this is to send up little tiny probes. The way they plan on doing this is they have a sail, a light sail that is very lightweight, very reflective, about a meter square, and you shine a laser beam from a 1 kilometer large telescope, and the laser beam is so intense that it accelerates this sail and this tiny little satellite to 20% of the speed of light. Okay? Very ambitious. We don't have all the technology for this, but this is probably at the forefront of getting to the next star system right now. And a lot of the technology is way beyond what we're capable of so far. A couple of seats over there if you want to. Yeah. Okay, so it's way beyond what we can do at the moment. Yeah. That's correct. We're giving it a shove, and then it just continues at that speed. And the pressure of the light is what accelerates it up to 20% of the speed of light, and then it's just pure inertia. It continues at that speed unless something slows it down. So unless it hits something. Okay? So even at 20% of the speed of light, it would take 200 years to get to Trappist 1, approximately. 200 years. Space is big and empty. Yes, so if it doesn't run into something, but space is big and empty. That's correct. And actually, there is stuff in between the stars, and I'll talk about that in a minute too. But big stuff is going to be rare. Okay? So, let's talk about where do we want to go. I think this Trappist place might be fun. Okay? First of all, there are 3 planets that are in the habitable zone, so that are the right distance between the planets and the stars, and the star, to have the temperature to have water, liquid water. And they're Earth-sized. And so this might be a good place for us to go. And if you want to hear more about the TRAPPIST system, I've got plans for an upcoming talk from another scientist here. So you'll have to stay tuned. Is that a pretty good, yeah, okay, good teaser. Okay. All right, so, well, now we know where we're going. Let's talk about our spacecraft. Okay? We're going to be in flight for, say, 200 years. Let's kind of think about the goal of 20% of the speed of light. We don't get, Einstein's not helping us out with time dilation just yet. We're still at 98% of, 98% time dilation. So we only shorten the journey for the travelers by about 2%. So that's not going to help. So we're probably going to need things like schools and houses and gardens with food and air and water. We probably need gravity. Because an entire generation living without gravity, we're already being cruel enough to these kids. They don't have the internet, right? Okay. So probably we want to have gravity. Well, let's think about gravity. There are 2 options. Option number 1, we could have our spacecraft accelerate the entire time we're going out there. And by doing this, we actually would get very close to the speed of light. In fact, you would get very close to the speed of light just between here and Proxima. But energy is going to be a real big problem, and trust me on this. Energy would be a real big problem with that. We're already going to have a problem with energy. But so I'm going to propose another option, is we rotate the spacecraft. So maybe we have something like this Stanford Ring. Okay? This is a ring, and then it spins around. And because it's spinning, this point here is accelerating towards the center. And since it's accelerating, it feels like there's a gravitational pull because the floor is pushing the person inward, pushing whatever's sitting on it inward, accelerating it inward. And so it feels like there is a gravity. And so I'm going to propose maybe we make our spacecraft something like a Stanford Ring. Okay? So, but let's go back to this energy problem that I talked about. How much energy would it take for an 80 kilogram person to go 20% of the speed of light? It would take 1.5 times 10 to the 17th joules. Notice that I didn't even bother putting the zeros. It's just, okay, this is too much energy for us to comprehend. This is, megatons of TNT. All right? If we fuse 229 kilograms of hydrogen into helium, with the efficiency of how much energy you can get out of that, including the neutrinos, everything, then you get enough energy to accelerate a person, to a typical person to that speed. And this ignores the requirement of action-reaction for thrust. And then we start thinking, well, we don't just need to accelerate a person there. We need their house and their school and their farm and their goats and, Okay, so a space capsule weighs about 5,560 kilograms. Ew, that's a lot of mass. And we need more than that. So energy is going to be a problem. But let's first talk about how a rocket works so that we can get over this action-reaction comment. Maybe that'll give us something. So imagine two identical twins on skateboards. Did everyone bring their imagination with them? Okay, then you see my identical twins standing right here, right? And you see that we're both on skateboards. Okay? Since my twin and I are the same mass, when we push off of each other, what's going to happen? We're equal and opposite. Yes. So we push off of each other and we both move back at the same rate at the same time. We both have the same speed and we both have the same energy moving away from each other. This is probably at the forefront of getting to the star system right now. My twin is smaller than me, half the mass. And when I push off on my twin, what happens? Conservation of momentum, right? The half mass person will go flying back at twice the speed. And how much energy? The moment. Yeah. It'll be twice the energy, won't it? Twice the speed, and it's squared. That's correct. We've got one of the students here that I've worked with here who's rather bright. I'm having him check my math to make sure that I've done it right. And so now you can go ahead and read that, Aaron. Did I get it right? Up to 20% of the speed of light, and then it's just pure inertia. It continues at that speed unless something slows it down. Unless it hits something. Okay. So, even at 20%, right, energy is not conserved. Percent of the speed of light. Yeah. It would take. Yeah. Well, 1/2 mv squared, and the velocity of the smaller is twice as large as the velocity of the larger. And so the velocity squared, 2 times 2, plus the 1/2 on the mass, so twice the energy. Sorry, everyone else is going, math. Shield me from the math. Yeah, Aaron's going, yeah. Doesn't run into something, but space is big enough. That's correct. And actually, there is stuff in between the stars, and I'll talk about that in a minute. Right. So the comment is, if we're throwing little pieces of mass off as a rocket does, then it creates a real problem for energy. So, we'll get to that in just a moment. So, yeah, and it's exactly right. So, more energy, when you have a smaller mass, more energy goes into the smaller mass. And so you can trade off mass efficiency for energy efficiency. Okay, so you have to strike sort of a balance between how much mass you throw off, because you've got to bring that mass with you, and how much energy you put into that mass. Now, when a rocket flies along, it doesn't throw off just one little tiny piece of mass. It throws off all the pieces of mass. It just does it one after the other, and it's, so they keep on flying off from the rocket, and so they all add up. But you're accelerating that mass as well. So you can actually get a little bit of leverage on it. But even then, the calculation I was doing here only took into account the energy that went into the person. So even if we're throwing off something as big as the Earth, where we can practically neglect the thrust mass, or the energy that goes into the thrust, we still need this much energy just to accelerate the person.
Okay.
Yes, we got a question.
We're going to be in flight.
We haven't talked about slowing down yet. That's exactly right. This is just to speed up. We need the same amount of energy to slow down once we get there. So multiply everything by 2 just to slow down, and probably by another 2 or 4 or 10 because of realities of rockets. And the conclusion is that, well, energy is a real problem here. Okay? And then on top of that, we need to remember that people need energy. We're about 80 watt heaters. But when you start thinking about 80 watts, which is 80 joules per second, or, that's tiny compared to what we're looking at to accelerate. So we can ignore that. But at any rate, energy is a problem. And if we're going 20% of the speed of light, anything in between us and our destination, any atom of hydrogen or helium, is now radiation. Alpha particles to move, I think, about 5% of the speed of light. So these are 4 times as fast, 16 times as energetic relative to us and our spacecraft. So we're being dosed by huge amounts of radiation. Our Geiger counters are going wild. So we need massive shielding. That's another big problem. Yes. So the question is, that she doesn't understand how that works. So there are particles of hydrogen and helium between us and the other stars. Just one every in 1 cubic centimeter. I was looking online and found that it's 10 to the minus 4th particles per cubic centimeter. Okay? So in a cubic meter, there's maybe 100. All right? So in a cubic meter, there's 100 particles. Now, they're just sitting there. We're moving at 20% of the speed of light. So relative to us, they're streaming along at 20% of the speed of light. And radiation particles, alpha particles, are the nuclei of hydrogen atoms. So these hydrogen atoms, of helium atoms. So these helium atoms that are moving past us at 20% of the speed of light are now alpha particles, because we're moving through this medium of them so fast. Does that make sense? But if we're doing the moving relative to us, we're moving right now, right? But we don't feel like it. And so if something were dropped in front of us that wasn't moving, we would be coming towards it very fast. But to us, it would look like it was coming at us very fast. So it's just all of your reference frame. And Aaron's over here probably saying Newtonian relativity. Mm-hmm. Yeah. Yeah. It's us hitting these particles. Imagine you're driving along on your motorcycle, and there's a bug. And that bug that bug feels like it flew at you, right? Even though you're the one driving. But in space, there's no absolute reference frame. So we're stationary. It's the particles that are flying past us. Okay? So in space, if we're going at a very high speed, we're getting dosed with massive radiation. So we need shielding. It's another thing we need to think about. Well, I don't think that we're going to be able to make it there with this approach. So let's look to new technology, and these come out of science fiction and other other stories. So some of the ideas are wormholes, and this is you make a tunnel through space that is shorter along the tunnel than it is between the 2 points in space. Maybe that could happen, but the calculations are that the gravitational fields along that tunnel would shred things. Tessering or folding of space is another one. And the idea is if space is like a fabric and you bring 2 points together, you can go the long way along the fabric, or you can just go from this point to this point now that they're touching. Okay? Again, this is far-fetched. Hyperspace is maybe there's a parallel universe in which we can jump into this parallel universe, and in this parallel universe, we can go faster than the speed of light. And so we go faster than the speed of light, get to where we're going, and then come back into our normal universe. Number of things wrong with this. First of all, we don't know it exists. Second, if it does exist, at least one of the laws of physics is different. What about the other laws of physics? Can we live there? Can we exist there? And so that's a little questionable. And then there's a warp drive, which it's still very far-fetched, but it's probably the most promising of these. And so let's take a look at that just for a moment, just to have fun. The idea of a warp drive is to shrink space, the space between us and where we're going. Okay, mass bends space, but mass tends to stretch space out, so maybe we need negative mass. I don't know. Okay, but we shrink space so that it's a shorter distance across these points. So these are all points in space, and all of these are normally parallel lines, and we shrink space so that now a meter stick going across here measures a shorter distance than a meter stick going across there. Okay? And then we can take our spaceship, fly across the shorter distance, and get there in faster time. Now, did I lose everyone on that? Because I think I lost myself. Yes. Mm-hmm. Right. Yeah. So, so this is the Ant-Man theory, is that right? So the idea that was just proposed is another one of shrinking people down to very tiny size, and then you can flick them very easily and accelerate them fast enough that they can get there. Maybe put them on the StarShot program, but or put them on an entangled atom or whatever. And yeah, again, some of the physics is there, not all of it, and it's very very far stretched. I mean all of these from what we know of the universe right now are pretty far fetched. Now we don't know everything. We may be missing some technology, but I still think that it's going to be a big deal to travel between the stars. I think Does everyone agree with me on that? Okay. So the conclusions our astronomer might come to is, first of all, that space is big. Did I say that space is big? I mean, space is big. All right. So, I mean, next time you're looking at that star, stop and think about how far away it has to be. And you'll sit there and boggle, your mind will be boggled for a little bit, and if you're like me, you still won't get it. But you'll get closer to understanding. Space is really big. The next conclusion is flying saucers. I don't buy that, because it's a big deal to come here, just as it's a big deal for us to go there. And if they came here, I don't think that they would go cow tipping in southern Utah and then leave. I think that they maybe they'll make a crop circle, but I still don't think they would leave. Okay, so one of the ways to get around the question, there was this comment that was made about how do you slow down after you get there, and one of the ways to do that would be you have this very large ship, dump that ship, and now you only slow down a much smaller ship for a shorter time. And that way, you can save, you know, big on your energy budget. And so I think that very honestly, you'd send the majority of your ship on, you just abandon it, hoping it didn't hit anyone, but space is big, so you don't think it will, and you'd get off. But now you don't have a return ship. So I don't think that aliens have visited us. I think they're out there. But even if they have this advanced technology, they're not going to come for just for short stays. They would come here and they would talk to us and they would interact with us. And the other conclusion is, if we're going to other planets, it's not going to be all of us. It's going to be a few of us to start a new civilization. The rest of us are going to still be here on Earth, and so probably is a good idea to take care of our planet for as long as we can so that we can have it and enjoy it as long as we can. Thank you. All right, any questions? Yes. Mm-hmm. Yeah. So the question is sort of leading in from Fermi's paradox of, if there's all these intelligent races out there, why haven't we encountered them? Well, it's very big. Space is very big and very hazardous to cross. And so one of the answers to that is that, well, you could send robots or computers and spaceships, but when they're going there, if you come across even a fleck of dust, you've got two holes in the ship. And the movies only show one hole, which is a very valid complaint. So yeah, that's very true. If you're going a large fraction of the speed of light, if you're going to go fast enough to arrive there in a meaningful time frame, a lot of you've got this radiation to overcome. You've got the micrometeorites, so dust is a problem. hitting larger and larger things becomes less and less likely. Um, but so Starshot, they're expecting to lose a certain fraction of the little spacecraft that they send out. You expect losses. You send out a lot of little tiny things, and maybe you can get there. And perhaps this is a good time to bring up the idea of sporogenesis, which is the idea that maybe the way to spread to other planets is not to send people, but to send microorganisms that carry DNA and get them out there. Because something little and tiny, like our Ant-Man approach to getting to space, might be able to survive that, might be able to avoid being hit by anything. Might. Okay. So we had, I think you were next, and then there and there. Hmm. Right. So sort of like similar to the original Contact in the movie Contact. Sorry to be redundant there, but so the question is, maybe instead of us going physically out there, we travel out there by way of information. So we could send instructions on how to build something so that we can interact with this other species that's out there. So have them build something to represent us to interact with them. And yeah, that might be a possibility. But you're still looking at 40 years round trip for the information to travel at the speed of light. Yeah, yeah. A meaningful information exchange, two-way exchange, takes more than a human lifetime. Yes. So, okay. Yeah. Yeah. So the question or comment is that some scientists are saying that within the next, say, 50 years, we will have figured out how to live for thousands of years. They're predicting that's going to happen. And so that could overcome a lot of these problems. Yes, in particular, the meaningful exchange taking 80 years, that certainly could overcome that problem. And possibly even how to get there if we're patient enough. But we still have a lot of energy problems to solve, even if we live very long lives. Yeah, 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 that's right. Would need to get away from chemical propellant, exactly. All right, we had a question over here, and then I'm coming back. I've got one there, and then back to you. Yes. Yeah, you. Yeah. Oh, so the solar system. Yeah. Where's So the question is about the slide I had that had the NASA um, uh, probes and that had been sent out. Whoop. Yeah, yeah. And so that's way back here. Give me a minute. We're getting there. Whoop. Everyone in the audience, the internet audience, is going. Wait, what? How did you rewind that? Wait. Okay. So, so yeah, there's the solar wind, okay, and there's the interstellar medium, and this where this stellar wind pushes around the solar medium, the interstellar medium, we kind of consider that to be the limits of our solar system, and there's a termination shock. So, in other words, that's sort of the boundary, and suddenly the wind is not strong enough, and you kind of build up this shock wave that's standing there. Yeah, where it dramatically, where the solar wind dramatically slows. And let's see, what else are you interested in here? Okay. Yeah, yeah. So yeah, what this represented is just the solar wind pushing out on the interstellar medium. Yeah, so we're in a bubble of solar wind, and actually, this solar wind protects us from a lot of things, a lot of the cosmic rays. Hmm. Correct. The radiation that comes in from outside, we get some substantial protection from that, is my understanding. And then, Aaron, you had a question. Mm-hmm. Mm-hmm. Yeah. So the comment that Aaron made is that the radiation in space, with respect to computers, that's a very big issue, and even computers that are at high altitudes here on Earth suffer from this problem. If you put a circuitry on, say, an airplane, you'll have that problem. And what can happen is you can have data corruption, you can have information being changed in the processors, you can even damage the processors. And the problem gets worse and worse as the computers get smaller and smaller because it takes less energy to change that, and to affect it. And it becomes more and more likely that a hit will do something enough to change that bit or to break that circuit. Okay, we had a question back there. Mm-hmm. Mm-hmm. So, mm-hmm. Okay, so the sun. So the basis of this is us becoming a Type 2 civilization, having enough, and so we build a Dyson sphere around our sun. Does the sun really have enough energy to move itself? Well, when we fuse hydrogen into helium, we get 7/10 of a percent of the mass is converted into energy. Okay, so we could move, 7/10 of the speed of light. You know, yeah. Well, right, but we're not converting the entire mass of the sun at one point. So in total, the amount of energy we get is 7/10 of a percent, and that's of the mass that fuses from hydrogen into helium. And so that's how much energy we would potentially have to get the sun moving. It would be enough to move. Yeah, yeah, but so yes, it's already moving, it's already orbiting. So the idea of using the sun as our spacecraft might be possible with a Dyson sphere level technology. Okay, it's but it's still a very long trip to go and visit the neighbors, even if you're packing up your house. So, all right. We'll go here. Mm-hmm. Yeah. Yeah, so one of the Voyagers recently left the solar system, and when I heard about that, I thought, hey, this is kind of like going to the Grateful Dead last Grateful Dead concert because you don't know if it'll be the last one. Um, or maybe that was the Ramones. I can't remember. Um, but yeah, it did leave the solar system, and there have been a couple of times before that they had said, "We think it's left the solar system." Oh no, not yet. And but this time they think it really has left, and by what they mean by that is it crossed the bow shock, and so they were no longer detecting the solar wind, and how they were converting that into sound, I'm not sure, but I think you're correct that they did try to convert that into a sound to play for people to listen to, and so the question is maybe it was the sound of particles hitting. I believe that's probably yeah they probably did something like that. So they would put it so they converted each particle hitting into some sort of sound element and putting that together, you know. Okay. Yes. Mm-hmm. Mm-hmm. Okay, so the question is that the universe is expanding, so is that how fast is that? And is that enough to affect the calculations for, say, the nearest star? Okay, the amount that the universe expands on, say, a galaxy scale is extremely small. Okay, they measure it in meters per second per kiloparsec or something like that. I mean, it's a very tiny fraction of the distance that we travel. So so right there, the answer is no. But beyond that, even if it was faster, what sets the distance between, say, the Earth and the Sun is not the expansion rate of space or anything like that. It's just the orbit, the gravity of the Sun, and the velocity of the Earth. So even if we were expanding enough that it would make a difference in the time we went to that star, we still would wouldn't it wouldn't affect us because the distance is set by the gravity of the galaxy and the rotation the orbits of the stars. But we probably do need to account for that rotation rate for those orbits because we're on a different orbit than they are. And if we're taking that long to get out there, we need to consider it more as an orbit transfer, a transfer orbit. So, mm-hmm, yeah. So yeah, the question is, could we look at a micro model of that? Actually, what we would do is we would model it in a computer. That's the best way to look at it. That's the simplest, most straightforward, and we seem to understand all the mathematics and the physics behind it, with the exception of dark matter, which is a little bit weird because we're still not entirely settled on what that is. All right. Any other questions? All right. Well, thank you very much. Appreciate you coming here.